Good morning. Welcome, my students, in the new week. How is everybody today? Good. Okay, I see the thumbs up. Thank you. Thank you, Lara. And I see also that you're using the chat, everybody's using the chat box saying good morning. Thank you. Thank you. Okay, that means what we will do. This week we will start calculus. We are starting chapter 2, and the plan is to cover 3 sections, 2.1, 2.2, and 2.3. Okay, that means today we will talk about section 2.1, tomorrow about section 2.2, and actually section 2.3 is recorded for you, pre-recorded, and you can check on Kasia's YouTube videos. Yeah? The link is provided on the front page, on the home page on Canvas. You probably know that page. Okay, that's mean 2.1 today. Let's start. I hope we had good pre-calculus algebra review last week. Yes, and we are strong, we are confident to start calculus. Okay. Actually, what calculus is? What is calculus? What do you think? Always seems to like everybody's taking calculus. Everybody's talking about calculus. Yeah, hopefully it's once per lifetime event, taking calculus 1. What do you think? What do you know, maybe? What do you heard? Like, what is calculus about? Any suggestion? Any, maybe just one word, maybe just some idea, because we cannot really studying math that represents the real world. Yes, because everything outside us is happening and we have to know how to define, how to model this. That's good. Higher level classes that you like use calculus. Yes, okay, okay. Okay, that means what we can say. First of all, we can say calculus is like mathematics of motion. Yeah, because talking about your comment, the real life, everything in real life is changing. Changing means like moving at a certain scale. Yes, and we have to know how to calculate these movements, how to calculate these changes. Yeah? If something is changing, we have to know, and we have to calculate, or we can say we can rate the change. Did you hear about something like a rate of change? Rate of change, you probably heard about this. That's yes, calculus is rating the changes. Okay, that means, but also algebra can calculate the rate of change. But we have a really, really important difference. That means let's maybe start talking about basic things because it's easy to apply. Let's talk about the speed. Speed or the velocity. Speed is it's the absolute value of the velocity is speed. Speed is always positive. Yeah? Okay, that we all know the formula for the speed. Do we know how to calculate the speed of the car or speed of anything? Walking, biking, driving. Yeah, like let's say, I can say speed. We can say distance over the time, correct? Oh my. Is somebody helping me? Let me just say distance over the time. Okay, distance over the time. Okay, that's for instance, when I'm driving and let's say I drove, my distance was 300 miles and I drove in what I can say, let's say 5 hours. And 300 miles took me 5 hours. That's what is my speed? Can you calculate the speed for me? Can you help me? 300 miles and 5 hours. Yes, nice and simple. It's 60 miles per hour. Well, we can see, we can simplify. Okay, that's it. And this is still rate of change. Yes, we're rating how the distance is changing with respect to time. Distance is changing with respect to time. Okay, that's me. Now let's maybe assume. And now the question is, I'm driving 5 hours, maybe from noon to 5 p.m. And do you think my speed at every single second was 60 miles per hour? Was I driving like all the time, constantly 60 miles per hour? When I will be looking, probably not. Yes, probably not. Probably I was driving a little bit slower and then maybe faster. Yeah, maybe I was speeding up. I don't know. Yeah, but 60 miles per hour that's mean, what is this? 60 miles per hour represents the speed, but what we can call? We can call that this is on the entire distance, that we can say average. Average speed. Okay, but now when I'm driving from noon to 5 p.m., I really would like to know what was my speed, let's say exactly at like 1 p.m. or 2 p.m. Let's say 1 p.m. Okay, at 1 p.m. What is my speed exactly at 1 p.m.? Like how we can, like when I'm driving and maybe I'm looking at the speedometer in the car, because I think the speedometer is using, yes, some calculus tricks, and it's constantly showing us the speed at that moment, at that instant. Yes, that means how I can calculate, like exactly at one point of time. I still need the distance, let me put distance, and I still need the time because this is the formula. But what is my distance traveled exactly at one moment? Yeah, it's yeah, we can say, yeah, Nathan, we can actually say 0. Because I mean, I can call distance, or I can call the position of the car, because we can actually I don't, okay, let me say, okay, it's 0. Yes, because yeah, if you will, for instance, take a picture of me, the picture is not moving unless it's the live picture. But on the car, even if I'm driving, you will, like, yes, you will take a like picture. The car is not moving, and then no distance. Yes, the position is not changing of the car, no distance. And what about the time interval? What about the time interval? How many minutes, how many seconds, or nanoseconds, microseconds passed for the 0 distance? Of course, 0. Okay, that's we do have a problem, and this problem is calculus. It's calculus. Of course, this is really symbolic, because I mean, first of all, that expression, that ratio, we will see a lot, or we will see in calculus. Yeah? It's we do have a special name. It's called indeterminate form, and we have 7 indeterminate forms in mathematics. We will learn them, but this is one of them, the first one. Yeah? And we actually know where this comes from. Yeah? Like if we would like to rate the changes at that instant, that means at that one particular moment, at that, yes, it's the whole story at that moment. That's calculus. How things are changing at this moment. That means at this particular moment, nothing is changing and no time passes, yes? But a second later, or maybe 2 seconds later, things are changing. That means, of course, 0/0 is, as I mentioned, is indeterminate form, and we cannot say that it's like undefined completely. No, it's indeterminate, and we do have a couple of methods, couple of techniques to figure out what is actual, yes, what is actual result, answer. But we will do this later. For now, we still have to know the speed, because probably like that 0 over 0 will lead us to a nice finite number. Maybe 60 miles per hour, maybe 50, maybe 80. Okay, that's what we actually doing. Oh, and one thing, this is still a rate of change. I mean, I can say the rate of change miles per hour, rate of change, but I will not call it average rate of change. Can you help me? If we calculating the rate of change at that instant, what is the name of this rate of change? Oh, do you hear? Did you hear? It's the instantaneous. We will call I think that's the correct spelling. Instantaneous rate of change at that instant. And yes, practically it's almost like 0 over 0. But what we have to do, we will still try to use actually the average speed, which means that we need a distance and we need a time, but it will be extremely small, like almost like, I don't know, a small rotation of the wheel, and we have to measure that a couple of like centimeters, couple of millimeters. And we also have to measure the time, probably 0.0000, I don't know, 1 second. Okay? That means in order to calculate this instantaneous rate of change, we still calculating this teeny tiny intervals, doesn't like intervals for distance, for time, or whatever we measuring, we calculating, and then we will get the answer. Okay, but that's the idea. And we do have a name for these tiny intervals. We call infinitesimally small intervals. Okay, let me write down. Yes, like we need the, it's weird word. Small. That means infinitely small. I can maybe say this, infinitely small, but it's infinitesimally small intervals. And then yes, and then we can get the speed. That means, for instance, okay, let's say it's not 0, it's maybe 0. That means infinitely small means that is almost 0. Yes, but it's not 0. I know, it's kind of like, that's what we will do. And okay, I will let you later. I will let you know later also another way for saying this. That means it is 0, but it's not 0. Okay, that's, we have to like kind of get this concept. Okay, that's, let's just say 0.006 maybe miles. And then what about 0.00? I want 60, because let's say my speed was 60 exactly at 1 p.m. Maybe this. When we divide, are we gonna get 60? I think 60 miles per hour. But we can see 0.0006 miles. I don't know, this is probably around like 3 feet. Oh, that's even too big, even too big. And this one will be 0.036 second. Okay, that's also a little bit. Yeah, 3 feet is still, we like need maybe half a feet, or maybe like, what's the scale for the small, like a milliseconds, maybe nanoseconds, maybe picoseconds. Yeah, I don't know the whole scale. Okay, but we can see we have to get really, really small, infinitesimally small intervals. Okay, and now you can see that means this basically represents kind of like 0/0. When we will see in calculus 0/0, we always have to think, okay, they are not zeros. Then you know they are not zeros, they are just infinitely small intervals. Like now I can say on the number line, okay, on the number line, we can pick a number that is not 0, but has 0 distance to 0. What is the number? Can you tell me? Again, on the number line, we can pick a number that is not 0, but has 0 distance to 0. Can you give me an example? On the number line, we pick a number, let's say A, that is not 0, it's not 0, but has 0 distance to 0. Yes, that will be good. That means 0 is somewhere, I don't know, 0 is here, and the number is 0.00000001, for instance. Or maybe on the other side, negative 0.00001. That means that's how we operate. And we still can create infinitely small interval. Okay, and if it's distance, if it's time, if it's number of some population. Yes, that means it's basically 1 to the power of big, yes, 1 to the power of big. And actually it's you say negative infinity because 1 to the power of infinity, this is another indeterminate form because I see somebody put on the chat box. Yeah, this one is different because this one will be 1 over, which is still 1 to the infinity. Yes, I know. It's also indeterminate form. 1 over 1 to the infinity, it will be also, the denominator is. Yeah, because 1 to the power of infinity is not always 1. Not always 1, but we will get later. For now, 0/0. That means now we know that when we see 0/0, it's not exactly 0. It's just teeny tiny intervals. Okay, that's me now how we can actually use this and how we can, because I can promise we do have lots of nice formulas, nice shortcuts. That means we can get quite quickly through this calculation. We don't have to always deal with all of this like zeros. Okay, we will get, but we have to understand the concept, because if you understand the concept, then you can solve everything. Okay, one thing before we move on. For instance, the Zenon paradox, I just copy for my students, just for your information, that everything is in rest. Yeah, motion is impossible. Because if we think about the arrow or about the car, when you're taking a picture, every single time the car is not moving on the picture. Yes, that means it travels no distance at that moment, at that time, at that instant. But then actually it is moving. Okay, you can read this later. Okay, before we start, I just want to make sure that my students will give me this. If I have number line again, and let's say value 2, and quite often I will ask you, please give me a number which is on the right-hand side at 2 on the number line. Can you give me the number on the right-hand side? Yes, and now this is, that's the thing. Maybe I can even, because I want the number, I want the number on the right-hand side at 2 means that we have to be really close to 2. 3, it's somewhere far away. Yeah, I just make the scale bigger to see this. That we can, we have to make again, the distance between 2 and the number has to be as small as possible, because that's how we will create that zeros or maybe infinity later. That means again, can somebody try again? What is the number on the right-hand side? Right-hand side, we represent with the plus, and yes, that will be an example, 2.00001 or even more. Yes, again, we can do this. Or maybe on the left-hand side, can you give me an example on the left-hand side? Again, the difference, the magnitude, the difference between them has to be really small, 999. Extremely small. Okay, that means that's what, yeah, like 3 will be far away. Lots of things can happen between 2 and 3. But when we are so close, this infinitely small intervals, then we getting this accuracy. And we can calculate 0 over 0. Okay, so now let's see. Let's look at a couple of information before we start actually the section 2.1. Okay, that in pre-calculus is more static, calculus is dynamic, it's movement, it's changes. I mean, we have changes and we have to calculate them, we have to rate them. I can also say that like pre-calculus algebra is the set of tools to solve the problem. Calculus is the set of tools to create a problem. Yeah, we're creating. And then we still need tools. We still need algebra, pre-calculus. Okay, that's we need pre-calculus. Then we will have this fundamental concept of calculus, limit process, limiting process. Okay, and then we will have calculus. Calculus has 2 branches, derivatives and integrals. We will talk about both of them in calculus 1. Yeah? But we will focus in chapter 2 on the limit process. That means this is this limiting procedure, process. 1.99999, we getting, but we getting closer, really close to 2, but we cannot actually reach 2. Okay, 1.999 or maybe 2.0001 or even closer. Okay, this means that limiting process 2 will be that limit. Okay, now I also have a couple of comparisons. What we can do without calculus, what we can do with calculus. That we can calculate the value of the function, no problem, or we can calculate the limit of the function. Okay, we can calculate the slope of the line, or we can calculate the slope of the curve. We can calculate the slope of the secant line, no problem. But what about the tangent line, slope of the tangent line? That's the topic for us today. Average speed or instantaneous speed? We kind of know what to do. That's calculus 3. Oh no, this we will try to get the maximum value. We will also need a calculus. Area under the curve. Okay, work done. If it's not, yes, if it's not the constant force, because if it's constant force, that's easy. But when the force is changing, okay. And other parts, yes, some volumes of the cylinder. We know how to do this, no problem. But when we have some irregular shapes, some solids like this, okay, then we will need a calculus. Mass of the solid, of course, yes, again, volumes. On the sum, if we have finite number of terms, we can add the sum. What about adding infinitely many terms? Do you think it's possible to add infinitely many terms? Are we gonna get a finite number? Yeah, this will be calculus 2. Okay, that's mean later when you will stay for calculus 2, we will figure out if it is possible to add infinitely many items and still get a finite number. Okay, you may guess that the answer is yes. Okay, that's me. Now we will try to get the limit idea, which we kind of know, based on the slope of the tangent line. Okay, that's mean the instantaneous rate of change, instantaneous velocity, and the tangent line. Let's start with the tangent line. Do we know what is tangent line? Do we know the definition or the meaning of the tangent line? Tangent line? Yeah, we probably understanding, because it's also important to know the tangent line definition. When two lines touches, Lara, that's really good. Yes, that's really good. The line that only intersects the curve at one point. Yes, that's the good definition. However, we have to be careful with this verb intersecting, because let's look at this one. This is the first touches. Yeah, touches will be better, but let's see why. It's still a good definition, but we have to be careful. By one of the famous mathematician, Leonard Euclid, he actually said, he stated that definition of the tangent line this way: the tangent line intersects, yeah, the same verb, the circle once and only once. And this works for the circle, because when I would like to find a line that is intersecting a circle only once, we will always draw a tangent line. We can see it's no other option. However, when we will take, okay, maybe too much. When we will take curve like this one, it's not a circle, curve C, and please tell me, line L, the blue line, is intersecting the curve once. Is the blue line, the line L, a tangent line? Because we have to really, yes, understand. Of course, yeah, of course is no. That we have to be, yes, we have to be careful. It's not. But now, that's definitely not. I will explain in a minute why this is, but we understand. Intuitively, we understand. Now, another important concept in calculus. What about the line, the pink line, the line T? Is the line tangent line to the curve C? Yeah, and now we can say yes, we can say no, but no, the answer is yes. However, we have to specify where we're looking at this. Where is that point of the tangency, if I can say this way? If we're looking again, we really narrow. We always looking at this infinitely small intervals, infinitely small neighborhood on the left and on the right hand side. That's when I'm only investigating point P, yes, the pink line, line T, is a tangent line because it's touching. Tangent from Latin means touching. Mathematically means that tangent line and the curve, they have to have the same direction. When we zoom in, we may see, when I will zoom in, when we will go closer and closer, we cannot distinguish the difference. We know that one of them is on the top, one of them is below, but we cannot distinguish the difference. They kind of like the same, indistinguishable. Okay, but the line, the blue line, we will always get. That's the curve, that's the line. When I will zoom in, we will always have this sharp edge, sharp like intersection. Okay, that means tangent line must have the same direction as the curve at that point. Sometimes we call slope of the tangent line, or we may say slope of the curve, because they are the same slope, the same direction. Okay, now you also answer no, saying that the pink line is not a tangent. Why did you say this? Because of the other point. Let's maybe name that point Q, for instance. Yes, when the line intersects the curve twice, what is the name of the line? Secant? It's a secant line. Yes, thank you. It's the secant line. But what's happened? This line is actually secant line when we look globally, but when we just narrow the vision, when we look at the point P, it's actually a tangent line. Okay, I think I typed everything. with we can say, yes, we can say parallel tangent line. It's parallel means like has the same direction. Yes, it has to just touch. Yes, we can say parallel because at that point, at that point P, that point of interest, point of the tangency, the curve and the line, they are the same. They are parallel. They have the same slope. We can say this, but the blue line, that's not tangent. This is just line intersecting once, but not satisfying the definition of the tangent. Yes, tangent line must have the same direction at the point of contact. Okay, and touching means just touching. Okay, we know what is tangent, we know what is secant line. And the line C. No, they will. Now is the question: does the point P and the line C occupy the exact the same y coordinates? I mean, yes and no. That between the difference between the y coordinates are almost zero. Yes. That means, yes, I like the really, 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 really close. This is actually in the y direction, but the y, yes, the y coordinates, they will be almost the same, really close. Yes, yeah. Close interval or open interval means that we not accepting. Yeah, like when we have an interval from 2 to 5, accepting 5, not accepting 2, that's what will be the number that we can accept, the first one that we can accept. That's the good, yes, good comment. Oh, no, 3 is far away. Let's say this is x. Yes, 2.0000001. We can accept this one, but we cannot accept 2. Yes, that's similar. Yes, similar concept. I mean the same. Yeah, 3 will be far away. We can accept the infinite approach. Okay, that's we learning this infinitesimal. Okay, that's me now. Example number 1. Yes, good. We have to find the slope of the tangent line to the parabola x squared at the point 1, 1. Okay, we have parabola, we have a line, I draw the line, and we have a point 1, 1. Now, equation of the tangent, tangent line is a regular line. We may use point slope form. I like to use point slope form because point is given usually. That means you may, yes, if you're taking some notes, you may remember that this form is quite helpful. Okay, we do have point. Oh, too fast. Okay, we definitely have a point 1 and 1 because we have point 1, 1. But what about slope? And this is the question, yes? What about the slope? How we can calculate the slope of the tangent line? Again, we will probably play with this small, because we have only one point. We cannot really compute slope between the point and itself. Because how we can calculate slope? What's the formula for the slope? Do we remember the formula for the slope? Oh, too fast. It's the changes in y, changes in x. Or we can say rise over run. Yes, or we can also say, because the changes delta y and delta x means y sub 2, y sub 1, x sub 2, x sub 1, the difference. But we can see we only have one point. I can call it x sub 1, y sub 1. We only have one point. Yes, that's what we have to do. We have to create the second point. Yes, we have to create, because we only have that point. X sub 1, y sub 1. We don't have the second one. But we remember, in order to get that, slope, that rate of change of the y values with respect to x. Otherwise, if I will put y sub 1 and x sub 1 here, we will get 0 over 0. And we recognize this. We know that we definitely have to make it to the, actually we don't, because I draw the pink line, we don't know, I don't know that point. Yes, I don't know any point because I don't have the formula. Yes, I know, looks, yeah, I just draw the pink line, but theoretically, we don't have the line. Yes, we don't know anything. We don't know the slope. We still don't know the equation. Mx plus b, that will be the b value. Yes, we don't know. We're working on m. Okay, that means we definitely know that we have to find the second point. Okay, but what I'm saying, point on the curve, not on the pink line, not on the tangent line. Okay, that's, let's see, I did pick the point. This is still 1, 1, and I did pick the point, actually value is 4, and I did pick the x, I did pick 2. Okay, that's me. Now I have the point 1, 1, and I have point 2, 4. Drawing a line, looks like I use the blue color. The blue line, we can easily find the slope. Yes, what is the slope between, what's the slope of the blue line between these 2 points, 1, 1 and 2, 4? Yeah, I think it's rise over run. I can substitute because we can nicely see. This is 3 rise, this is 1 because it's 2. It is, the slope is 3. Okay, but what's happened? Blue line is not exactly like a pink line, but we did calculate. We can see, we use the algebra, we did calculate. But please correct me, what I did maybe not exactly that I supposed to do. Because I did pick, this was the x value 1, and I did pick 2. I picked the point Q with the x coordinate 2. Do you think that's good or that's not? How we can actually improve that calculation to get better approximation of the tangent line? We have to change the point Q. Definitely. Point Q must be different than point P. We cannot get 1, 1 because we know when we get 1, 1, the slope between 1, 1 and 1, 1 is 0 over 0. But we know that it's not, 0. Okay, that's how we can improve the point Q. Can you give me an example? Is 2, is the quantity 2? Yeah, yes, it's not close enough. Yes, we have to, because what I create that changes in x too big, 1. Yes, that delta x, 1. And I have to create teeny tiny, yes, infinitely small interval. That means not 2, maybe not even 1.5, not even 1.1, 1.01, 1.0001. And then I can repeat the same calculation. Okay, that means 2 and 2, 4, that was far away. And I think I have this nice picture. We can see this is 1. I did pick 2. This is 1.8, maybe 1.5, 1.4, but I need even the point Q to be here, 1.01, let's say. And then when I calculate the slope of the secant line between 1 and Q, between P and Q, it will be almost like a tangent. Okay, that means, let's see, I did use calculator and I have the calculation. I picked the point 1.5, 1.1, 1.01 for the point Q. Point P is still the same. Okay, and then when we have 2 points, we know how to calculate the slope. That's, let's see the calculation. This is just the difference, delta y over delta x. The slope of the blue line for the first picture is 2.5. For the second is 2.1. For the third one is 2.01. And what do you think? What will be the approximation? How these numbers behaves? Yes, I think they getting closer and closer. I mean, now just the slope. They getting closer and closer to 2. Yes, almost. And we may notice how small this was. The delta x was 0.5. Delta x was 0.1. Delta x was 0.01. We making this interval infinitely small, and we can even keep getting closer, keep like making this delta x smaller and smaller. And that means this is the way to get the slope at the moment. We will get some fast way. I also did the calculation on the left hand side. Let's see, 0.5, 0.9, 0.99. Okay, and the slope, and we can see how the slopes behaves. 0.5, 1.5, 1.9, 1.99, and definitely is approaching 2. Okay, we have a slope of the tangent line to the parabola x squared at the 0.11. It is 2. Okay, let's look at that. I think one of the homework assignment, it's asking you to actually pick this couple of values and calculate something. Okay, that means and for this one, we can use calculator. We can use the calculator. Okay, let's look at this nice statement. The slope of the tangent line is the limit of the slopes of the secant line. That means whatever we did on the last 2 slides, this was this limiting process. Yeah? Like even, Brian said it tends to approach 2, tends to the 2 value. Okay, this is important. Okay, this is one of the important message on the first section. Now, how we can use this limiting process using some symbols. Okay, that means the whole limit process, we will not write the whole word limit, we will just say LIM, limit. And limiting process, we always have to say what we're limiting. This is the slope of the secant. Okay, that's the slope of the secant line, QP. And underneath the word limit, LIM, we have to show what actually was like approaching what. That means Q was approaching P, the coordinate of the axis. Yes, the Q was approaching P, was getting closer and closer to the point P, not exactly P, but we know close enough. That means this is the nice limit, but what we will also do, we will rewrite everything in terms of the independent variable x. Let's look at this. That's the same thing. That's the same thing. This means the slope of secant. Yeah? Because that was the coordinate of the point P, 1, 1, and this was the coordinate of the point Q. Yes, Q, like if x was 2, the y value was 2 squared, 4. If x was 1.5, what is 1.5 squared? 2.25, I think. Yes, then we will have squared. That means this was the coordinates of the Q, this is the coordinates of the P. The whole ratio is the slope of the secant line. Okay, maybe we don't need all of this. And now, please note, the x coordinate of Q did approach 1. Okay, that's when we have a nice limit settings. All of the parameters, all of the components. And it's equal to, now, this is also important. Of course, I'm taking that too because we did the whole calculation. And also, please note that it's the equal sign. It's not the approximation, it's the equal sign. And we will always say the limit equals to. The whole concept, we have to always remember that is sitting behind that limit. That's when we understand that this is still like kind of like approximation, but this is taking care of this. We will still say equal to. Okay, because sometimes students is asking me if we can put the approximation. No, we can just put equal to. Okay, and I think I have just the tangent line. When we use the point slope form, slope, point, and when we solve for y, rewrite in terms of x for y, it will be 2x plus 1. Oh, is that correct? Please check if this is correct, because negative 2, of course, because do you remember that y-intercept? Somebody asked if we can, of course it's supposed to be, let me come back for a second. I mean, we can come back even here, because we can see it's negative value. The y-intercept. Oh, you see, that's the skill to correct yourself, which is difficult skill. Okay, oh, too fast. Okay, this is -1. Yeah, because it's -2 plus 1, -1. Okay. And because we had this y-intercept on the below the 0, below the x-axis. Okay, that's the tangent line. That means this is important. That table is important. Yeah, just remember. Okay, really quickly, we can look at velocity. We talk about this. We start the whole conversation with the velocity. Average speed is not a problem, but the instantaneous rate of change, instantaneous velocity, instantaneous, I mean the rate of change at that moment, yeah, how we can calculate. Okay, that's the average, that's not a problem. That means the slope of the secant line will also represent the average rate of change, just rise over run. And we can say average velocity if y represents the distance, and on the x-axis we have time. Yeah, that means slope of the secant line, it's the same like average velocity. It's worth to remember. That means this is the second message. It's the first one, second message, slope of the secant. If we have to look at the average change, average velocity, average rate of change general, we will just draw 2 points, rise over run. It's like a slope of the secant. Margot, what do you mean always the second line? I don't know.
There's a situation where, like, for some reason you need the first line involved in that because you're saying the second line. Like, how do you tell if it's the first or second line? If I missed that just because I came late, then my bad. But because sometimes, when you're working with functions, like sometimes you're looking for one part of the line and then you need to look for the other one. So I'm just wondering if it's like that.
Oh, you mean the second line, you mean secant or tangent? Because I don't know what you mean
Well,
by...
I see 2 lines on the screen, the blue one and the black one. So I'm wondering if you mean by second line that, or if you just mean tangent, or like visually what you're looking at.
Okay. On this screen, the black one is the curve. It's just the function.
Oh, okay. Just checking.
Okay, that means the blue line, I just pick 2 points and I connect these 2 points on the curve. Okay, maybe this one looks like a line, but no, it's kind of like, it's like parabola.
Gotcha.
Okay, that's me. Okay, the blue line is a secant line. Yeah, secant line intersects the curve twice. Okay, but now looking like, I mean, taking the same concept, let's look at the tangent line. Yes, when we have a slope of the tangent line, which will represent the instantaneous rate of change, okay, calculate calculating that instantaneous speed, instantaneous velocity, we just have to calculate the slope of the tangent. Okay, that means this is like another message. The third one, we have three tables, three boxes. Please know all of them. That means slope of the tangent line, which we know how to calculate. We did the long process, but we know, at least we know. It will be exactly the same idea like calculating instantaneous velocity. Yeah, that's what we can see. If this is my, let's say that curve, it's the position function, okay? Like at one, let's say it's hours. At 1 hour, when I follow this formula, it will be 10 times 1 squared, it will be 10 miles. What about 2 at 2 hours? What is my distance at 2 hours? 10 times 2 squared. 40? Not that, yes, no. Oh, maybe I'm wrong. No, no, good. Okay. Yes, yeah, that's correct. That's what we can see, we can calculate, but I don't want to know my average speed, average velocity. No, I would like to know the speed, the velocity exactly at 1. Yeah. Then what we will know, like how to solve this problem, if this is like physics problem, application problems, then we know, okay, I have to draw a tangent and I have to find the slope of the tangent. That means the instantaneous velocity, it's the instantaneous rate of change in general. It's the same calculation like finding the slope of the tangent line, because we only have one point of information. We have to create the second one, teeny tiny interval, and then we know the process. Okay, but please remember, instantaneous velocity, slope of the tangent. Average velocity, slope of the secant. And now, if you can answer this question, we can finish the session. Okay. I have a graph. Everybody is ready. Let's say y, x. Use the sketch of y equals to f of x below to find the sum, okay, sum is not a problem, of instantaneous rate of change at 7 and average rate of change on 0 to 2. That's we need the we need I cannot write. Okay, I wanted to underline this, but I cannot underline, I don't know why, higher. We need instantaneous rate of change and we need average rate of change. Okay, what is instantaneous rate of change at 7? Looking at this model. Okay, everybody is answering. Do you remember, we just have 3 boxes that I ask you to like, yeah. Okay, reset 0. Can somebody back up that claim or maybe is, I mean, slope of the tangent? Yes, this will be, no, let's use that slope of tangent line at 7. That means this is 7. And when I draw tangent, based of my knowledge of the definition, looks like this. That looks like a horizontal. That was at least the intention. What is the slope of horizontal lines? Yes, that means this slope is 0. This is the instantaneous rate. And because I just want to stress this out, instantaneous rate of change is like slope of the tangent. Yes, it's actually 0, not changing. Yes, when you will look at the big graphs and then somebody will say, oh, how the situation is changing on 7th day. And you will say 0 is not changing. How do you know? Oh, I know, I took calculus. Okay, that's, you see how nice. Yes, you know, that means actually situation is not changing. Oh, actually nice, because the 7th day, let's consider that Sunday, we like having, we relaxing, we're not working. It's the situation is not changing. due to, I mean, no, doesn't, you mean like looks like a maximum value, like locally? Yes and no, but we may, yes. No, the highest peak will always be 0. We have to be careful because when we have function like this, for instance, and let's say this is 7, but we will, yes, we will learn this, I don't know if, no, probably later. What about tangent line? Can we define a tangent line when we have these sharp turns? Because looks like the highest peak, but it also depends on the shape of the function. Okay, do you please help me. Do you think we can draw the tangent line here? Because based on the definition, we will never be able to draw a tangent like this, or maybe like this, or like this. We will never draw a tangent that will have the same direction as the curve at the point 7, like in case of that sharp turn, like the sharp peak. Okay, that we have to, yes, we have to be careful with this terminology. At the moment, yeah, I mean, when we have this nice smooth curve, yes, when this will be like a maximum value, always the instantaneous rate of change will be 0 because the slope of the tangent line will be horizontal. Okay, that's me. Good, yes, good thinking, but we still have to be careful with different shapes. Okay, we have 0. Would the maximum of the curve always have a slope 0? No. No, I just said because when we have this function with the sharp corner, that's not actually the slope of the tangent tangent line doesn't exist. Yeah, that means this is the peak. It is a maximum value, but slope of the tangent doesn't, because tangent doesn't exist, then slope of the tangent doesn't exist. Then instantaneous rate of change doesn't exist. Okay, good, yeah, good thinking, but please, yeah, please just focus at the moment on the rate of change, not the maximum value minimum. This one. And please tell me what's the average rate of change between 0 and 2, and we will finish. We will continue tomorrow. It's just, yeah, 0 is here, 2 is here. We basically have a slope of secant line. Yes, and you can say it's -2 or -1. 2 and 4, I think it's, oh, please confirm. I think it's -2. And the sum will be 0 plus negative. Yes, it's -2. Okay, that means the final answer for this question is -2 because 0 was the instantaneous rate of change and the average rate of change was -2. Okay, that's let's just finish with with this concept: instantaneous rate of change and the average rate of change. Slope of the tangent line, slope of the secant line. That's it. Okay, thank you very much. And we will talk about this maxima minima later. And we will connect this concept. Okay, thank you very much. And please join me tomorrow. Please join me tomorrow. Tomorrow we will take the limit concept, and we will go deeper in this to understand from different angles. Thank you. No, not fun. I mean, we definitely need a little bit of time, yes, to digest this. But this presentation is nice. You can look at this presentation one more time. Okay, thank you. See you tomorrow.